Hello and welcome to this, the 23rd edition of the IoTSF monthly webinar, which means that as of next month, if you wanted to binge watch the entire back catalogue of recordings, you could literally watch them all day. However, the only way that you can watch the back catalogue of these webinar recordings is in its entirety is to be an IoTSF member, either as an individual or as a company membership. So go to IoTSecurityFoundation.org/join if you're not already a member in whichever capacity. You can, however, watch shortened videos of our past webinars on the IoTSF YouTube channel, which has also got a feast of other good stuff, including past conference talks. I'll put the relevant links in Zoom chat in just a couple of moments. So coming up on today's broadcast, we'll have full stack IoT security from core to edge with Peter Cox of Labs. But first up, it's John Sirianni, who is the CEO of Tropic Square. At the 2024 IoTSF annual conference in London this past October, I was running around all day in the background, but one of the talks that I did manage to catch was by John Sirianni. And I was so impressed that I actually asked him if he would be a webinar guest, so I'm delighted that he joins us today. John is about to present on securing next generation critical infrastructure with open and auditable hardware. We'll explore the critical challenges of securing next generation decentralized infrastructure and introduce a transformative approach to hardware security architecture. He joins us now from London. John, the floor is yours.
Good afternoon, Chris, and thanks for the invitation and the very kind introduction. It's good to be back in London. I have a presentation that I'd like to go over to bring forth a new paradigm that's emerging in the open source software market for chip development. That's open source hardware, and why we started a company devoted to higher degrees of security using that technique. So with that, I will launch into a presentation. One moment. And are we coming through?
You are, John. You're good to go.
Okay. So the title is Securing the Decentralized Future. And underscoring that is a paradigm shift between a centralized infrastructure of the past and why and how we're moving quickly into a more decentralized infrastructure and why open and audible hardware security is needed for the new forms of IoT and integrated Web3 ecosystems that we'll all be working on in the next few years. So as mentioned, my name is John Sirianni, Chief Executive at Tropic Square. Tropic stands for Truly Open Integrated Chips. We're a fabless semiconductor company in Prague, Czech Republic, launched in 2020. We are now in production, and what I'd like to share is some of the genesis of why we took this approach and what it means to designers of decentralized platforms. So the four major topics we're going to be going over today are how IoT infrastructure is transforming and merging with decentralized open ledger platforms, why cryptographic handling now is even more critical to the next generation of decentralized IoT critical infrastructure, why also open and audible semiconductor solutions are best suited for this next generation of infrastructure, and lastly, how an open community-driven innovation method is best for accelerating hardware security. So we're going to go through a few slides here that characterize some new buzzwords that we've all been hearing for quite some time. One of the trends within IoT is the merging between edge systems and blockchain data structures. So as many of you know, blockchain is the foundation of the crypto industry, and it's many projects that we have being developed today. There's a phrase being called transactional IoT. You may have heard end-to-end payment systems. You may have heard the Web3 of things. You may have heard decentralized physical infrastructure. They're all pointing to the same thing, which is the integration of traditional IoT systems with blockchain secure data structures. So as a quick review, when we say blockchain and decentralized ledgers, what we're talking about as a review of what blockchain is a decentralized shared database. The blocks of transactions are linked or chained together via cryptography. These tend to be peer-to-peer networks and are driven by agreement protocols and very autonomous. We can have permissionless or permissioned systems, and generally all records are securely replicated and stored across the decentralized network of computers that participate in the system, typically called nodes. It's been proven fault tolerant even against large-scale attacks and provides transparent, open, immutable, and trusted, and tamper-resistant, secure transaction ledger architectures. So it's been proven the last 10 years that these systems are very, very secure. And what's not secure are the edge devices that interact with them. Now, why is this more important than an old school traditional IoT? So what I'm showing in this slide is somewhat of a comparison between traditional IoT that we've known and loved for the last 20 years and what has become transactional. So in a traditional system, data security is very centralized. In a transactional IoT system, we're talking about decentralized. Here's one of the key elements: transaction settlement speed. In a traditional IoT system, it depends on the intermediaries involved in the system on how transactions are settled. It may be many days in a banking system. It may be 24 hours within an industrial system. But in a transactional IoT system, access into a blockchain means instant settlement, because the ledger is the record of all transactions that have occurred up to that moment. So there's no reverse. There's no redo, right? There's no undo button. And so the settlement is instant. Costs are very high and traditional. And the hope in the transactional IoT systems is very, very low transaction costs due to automation. Transparency can be very limited in traditional IoT systems, and the very foundation of transactional IoT is open system. Scalability in traditional is one-to-many with single points of failure, and DDoS attacks tend to be the predominant system failure mode. In the transactional IoT, these are peer-to-peer and many-to-many relationships and are extremely fault tolerant. And lastly, compliance and governance. In a traditional IoT system, we see that the industry frequently lags, regulation frequently lags, and it takes many years and even decades for the two to align, if ever. In a transactional IoT system, it's open, audible, and automatically compliant. More about that when we get into this a little deeper. So let's compare and contrast an architectural point of view between these systems. The traditional IoT systems of the past have been hierarchical in nature. We're moving to autonomous and smart contracts. And for what that means is we're moving from a centralized authority enforcing trust between parties to protocol-defined self-executing agreements. And this is what is referred to as distributed apps or DApps. We're moving from centralized networks to peer-to-peer decentralized systems. This is from centralized administrators holding copies of digital transactions that happened in the past to blockchains that are keeping a live chain of all digital transactions in the system. And at the device level out on the edge, we're moving from connected things to immutable things. So from what we're saying here is from centrally connected individual devices to immutable device system trust. Now, before we get into some use cases, I'd like to just provide a little bit of context on where some of these terms came from. It might be helpful in understanding where we are and where we're going. Back a long time ago, early in my career, we had Web 1.0, read-only, very static web pages and websites. Around 2004, Web 2.0 emerged, and what we then became to understand and expect is that we had read-write capabilities in the internet. It was very interactive. It's based on an advertising business model. Centralized platform power became the dominant force in the business model. The threats became mostly to the centralized targets because that's where the power was kept. And what funded it was a surveillance economy. Everything you do was monetized, copied, and monetized. As 2014 came along, I was working in Silicon Valley and saw this emerge in real time. The definition of Web 3.0, which started at that time, was that the web would become an intelligent semantic system and context aware. Now, context aware, what is that? That's, hey Siri, hey Alexa. It's semantic, it's intelligent, it's context aware. It can interact with us in real time. This is when we began to see machine learning and early AI systems develop. And then spin forward to today, we're seeing AI at the edge. What then also occurred at that same time in 2014 was the definition of Web 3, not 3.0. And this was brought forward by the crypto enthusiasts. This was a read, write, own business model. You own what you publish. Blockchain-based digital ownership, decentralized peer-to-peer, cryptocurrencies, decentralized finance, smart contracts, distributed autonomous organizations. All of these things were put on the table as what the future would behold. Today, 10 years forward, we've seen a blending of Web 3.0 and Web 3.0 and all of these terms into a very unique and system of participants that's only just now beginning. And what I'm referring to is the decentralized physical architectures merging up with the traditional internet architectures. So what we're starting to see in some use cases, for instance, fractional ownership of physical gold, tokenized. So the concept of using paper and a stamp and a government authority or an office to notarize and certify the officialness of something is very quickly being replaced by crypto secure algorithms and distributed applications. We're beginning to see non-fungible tokens and smart contracts play out in real estate. We're beginning to see supply chain transparency. We're beginning to see tokenization of energy in the energy grids. And lastly, digital wallets have been something that have been developing and evolving over the last 12 years. And this is what the use case we're going to dip into, the digital wallet, as an example of transactional IoT. So transactional IoT, more than anything else, requires cryptographically secure elements in the system because value is transmitted instantly. The use case we're going to talk about today is that of the crypto wallet. Some of you who have bought and held crypto assets over the years, you may have taken custodial ownership of your crypto keys. You may have kept it at an exchange. If you take ownership of your keys and keep it on a device, you're expecting that that device can keep the private keys secure from all forms of attack, online attacks, physical attacks, things of that nature. So hardware wallets are in fact transaction endpoints that securely create, store, and manage a user's private keys or their assets. Devices interact directly into a blockchain infrastructure. Private keys in the device control value transactions, and the hardware storage of private keys needs to be kept very secure against online attacks, physical attacks, side channel attacks. And so the piece of silicon that ensures that this happens inside these devices, and I have some devices shown below, is something referred to as a secure element. Those of you in silicon and architecture design generally know what these are. The device pictured on the lower left, or at the left of the three devices, Treasure, is the device that was designed back in 2014 from our parent company. Our parent company is Satoshi Labs, and they're the developer of Bitcoin mining technologies and also crypto asset wallet technologies. They saw the need for something different in the silicon industry. And what we're going to share here with you on this slide is what the developers of that crypto wallet discovered. They They knew they needed a secure element to be able to ensure that the crypto wallets were secure against all forms of attacks. What they first discovered was that secure elements that they could get in the marketplace in that time period were indeed hackable. There was no special equipment needed. Keys can be stolen, and so the first thing they learned was not to trust just a chip that comes from a vendor just because it has some certifications. The second thing they realized when they looked into even better certifications for secure elements is that the certification stamp really didn't mean anything. Attack testing wasn't relevant to the type of attacks that aggressive attackers were using against crypto wallets. So in each industry, we see different type of attack techniques. The implication there was not to trust. And the further lesson learned was independent testing is always required. The last gotcha that the team stepped into was that the semiconductor industry at that time was very proprietary. So all of the intellectual property was closed, features were hidden, not very well documented, and there really was no accountability. What this meant was that if you as a developer found a attack vector that was present, you really couldn't tell the community about it because you signed an NDA. So closed architectures were by their very nature risky and falling behind what the market needed, at least what this segment of the market needed. So the teams thought, obscurity doesn't work. We need something that's a little bit more transparent. At the same time, what was happening in the industry is that the semiconductor attack methods over the last 10 years were getting much more aggressive. Laser fault injection, EM probe listening, and voltage glitch were common. But what was happening was that those the equipment required to carry out those attacks was getting progressively less expensive. And more researchers were able to carry out those attacks successfully on secure elements and expose the keys. So the team went back to the drawing board, and I'm going to talk about two principles that have been with us for a very, very long time in cybersecurity. And the question that they asked themselves was, can these principles be used to architect a perfectly secure system? So principle number one has been with us a long time. Augusty Kirchhoff, he's hard word to say, Kirchhoff. His principle was that the security of a crypto system must lie in the choice of the keys only, and everything else, including all algorithms, should be considered public knowledge, right? So no matter what you design, it's considered public knowledge. So you need to keep the keys safe. Claude Shannon came along, and his maxim put that thought into more rudimentary practice and said one ought to just design systems under the assumption that the enemy immediately can gain full access to them, right? So if we take these two principles as guidance, can we make security through transparent in a way that keeps the system safe? Can we, in fact, create a transparent, secure element and keep the keys safe? And that's what the team set out to do. So the graphic on the right is the exploded view of our chip. It's a 4mm square, very small package that is now shipping. And what the team set out to do was create a RISC-V open architecture solution, open software and open hardware, that took some principles that put Kirchhoff's principles and Shannon's maxims into silicon. And so what does that mean? So our crypto coprocessor is a coprocessor. So it's a SPI connection to whatever MCU or CPU you have in your system, and it just performs the crypto coprocessing. That is the development, storage, and management of the crypto keys or customer private data. Three different principles brought down into silicon. The first one is zero trust in circuit. So what this means is that we have cryptographically secured every circuit in the chip that handles the customer's data or the cryptography management functions. So this means that we're protecting the cryptographic engines themselves in the chip from side channel attack. We're protecting the secure channel that we're using as a noise framework, and contact us. We can get into more detail on what that is, but that provides perfect forward security at the chip, at the IC level. And we're generating entropy on board. So we have two true random number generators on board in each chip. As far as supporting firmware upgrades in field, we have a PUF, physically unclonable function, on board, advanced user pin management and recovery techniques, physically tamper resistant against laser glitch and EM listening, and a very minimized attack surface. So this is a very specific ASIC designed for crypto co-processing. This ensures continuous security. How? We have transparency in the community because we're putting all the IP out on GitHub. You don't need to sign an NDA to be able to have access to the IP. Everything that we have as far as crypto engines and algorithms and curves is upgradable. And we make all of the testing results public. And we encourage those that test our chip to do the same. Looking under the hood, these are some of the features and functions I'll talk to at a very high level. Contact us if you want to get into more detail, or you can download the data sheet on our website. So as I mentioned before, tamper resistant. We do all have active shield on there as well. We have quite a few cryptographic accelerators, and they're all of them that are listed here are chosen for very specific purposes, optimizing speed and security. Entropy sources, we talked about those as well, PUF and TRNGs. It's a RISC-V IBEX controller. The memory is one-time flash, and we have a lot of techniques in how we protect the memory as well. And the rest of it is more detail that we can discuss over a data sheet and a cup of coffee sometime. Just contact us. The open and transparent nature of what we do enables quite a few design benefits. You can use this technique for system root of trust, device authentication and attestation. This technique also allows for digital sovereignty. And this, what we're referring to here, is the use of ledgers and public ledgers while having the source of the data and the key handling at the edge to be very, very secure. So this enables the promise of digital sovereignty that goes around with open ledgers to actually be manifested. And this invites the community to test and to publish the results of those tests. It invites the community to develop on top of what we've built. An open architecture ensures future-proof adaptability. We don't limit what can be done with this IP, and we expect it to be used by others. We expect it to also drive faster time to market for developers. The CRA, the Cybersecurity Resilient Act, has made a lot of press in the last year or so. Fundamentally, to an open architecture design is that all participants in the ecosystem can then articulate what is secure and what is not secure about these solutions. The EU cybersecurity rules that are focused on more secure hardware and software products articulate two very important critical infrastructure device classes. The first are smart cards and TPMs as critical products. And then also important products are firewalls and tamper-resistant MCUs, routers and CPUs. These categories are mandated going forward to be transparent and open, to have secure elements, to provide better understanding of vulnerability, and also better governance. And so it is our expected belief that these requirements will drive more open software and hardware systems. So it's about finishing up here. Key takeaways for new security paradigm is that secure decentralized ledger infrastructures and traditional IoT infrastructures are beginning to merge. Attacks are becoming more advanced on less costly to carry out, which drives the need for better key management in all IoT devices and drives the need for faster innovation in silicon-based security. Security through adaptability is essential in this fast race as we begin to put more systems at the edge that are AI enabled. Open source and open hardware and security becomes essential. Open community security testing and open sharing is necessary. And all of these address cybersecurity resiliency. So security through transparency or open IP, not obscurity. That's what we're about. We will be at the Embedded World Conference in Nuremberg, March 11th through 13th. We are now in production. There's a picture of our chip under test. Feel free to give us a call if you'd like to get into the technology a little bit deeper. Happy to share that with you. And thank you for joining.
Thank you very much indeed, John Sirianni. So TechWorks AI is a sister organization of the IoTSF, and it's going to be holding an in-person event on Tuesday, the 25th of February at England's Bletchley Park near Milton Keynes. The event is entitled Engineering Trustworthy AI from Concept to Reality, and it'll have speakers from Amazon, BAE Systems, and the University of Oxford, to name just a few. The event is free, and you can register now. I've put the link in Zoom chat if you're watching this broadcast live, or go to techworks.org.uk and go to the events section if you would like to register for that one. So if you've got any questions or observations after watching John Sirianni's presentation, please put them in Zoom chat and we'll address those during the Q&A at the end. Already got quite a few questions coming in for you, John. IoTSF members will be aware that we've been raising the awareness about the importance of memory safety in relation to cybersecurity. We've been involved in collaborative projects with our members and Res Auto, which is an automotive-based project, and Secure Networking by Design, otherwise known as SNBD, which is router-based security. And so we've just last week published a global marketing report on cherry-based router and connected device infrastructure. You can download this report for free. I'll put the link in Zoom chat, or go to the publications section of the IoTSF website, and that's got an abundance of other good stuff, including our famous assurance framework. So 2 other things to mention quickly. Our next webinar takes place on Thursday, 27th of February. We'll be talking cryptocurrency with Temple Melville of Scotcoin, and we'll also hear about the Cyber Resilience Act compliance wizard, otherwise known as Krakawi, and that's from Dusseldorf's Michael Beiner of Bureau Veritas. You can register for that one now. I'll put the link in Zoom chat, as is customary. And if you watch it, if you're not watching this live, if you're watching the recording, go to the events section on the IoTSF website to register for that one. One last thing, and quickly, the IoTSF has chapters in Bucharest, Bangalore, Houston, Texas, Chennai, and Amsterdam, but we soon hope to have one in Melbourne. So there's going to be an expressions of interest event in February to get the IoTSF Melbourne chapter going. So if you're in Melbourne or within traveling distance, it takes place on Wednesday, the 12th of February, 6 p.m. till 8 p.m. AEDT at Library at the Dock. It will feature a practical presentation by Michael Lindsay of Blueside, and the event is completely free, and there'll be loads of networking as well. So that's an expressions of interest event for IoTSF Melbourne. If you know anybody in Melbourne who you think might be interested in that one, then please do let them know. So onto the Q&A section of today's broadcast, and John, I guess I'll start.